Confidence intervals, topic of the day. I'm excited about this one. You're guaranteed to love this video. We have been discussing sampling distributions. What happens when we repeatedly choose samples of a certain sample size from a population? We talked about how they're normal. We talked about their shape, center, spread. We've found normal calculations. And here's an example. I want to start with just a few articles I found, and I've highlighted some statistics. Less than half of Americans have performed a calculation to determine how much they need to save in order to retire. How do they know that? Well, they asked some, and they got some amount less than 50% of people who said, yeah, I've done that. A statistic. Do they really know that? I'm not saying they're liars. I'm just saying they didn't ask me, so how do they know exactly what that number is? This is a statistic. Another one, nearly half of adults over 40 who have asthma still smoke. Did they ask every adult over 40 with asthma, do you smoke? Did the people who they asked tell the truth? We don't know. These are statistics. They have variability. This is the one I'm going to focus on for this video. The hourly earnings of production and non-supervisory employees. So not the boss, but the grunt workers. They average $20.70 per hour. All right, so we're going to focus on that one. $20.70. Let's just say everything in white here is stuff we don't know. I've been saying a lot of that. These are numbers that we do not know. We have to learn this stuff assuming we do know. All right, so in reality, this little blue dot is the only thing I really know. I am going to assume that the hourly wage population looks like this graph in white. I don't know what that really looks like, but I'm guessing it has a right skew, and I just made it funny looking to prove a point. If we make a sampling distribution, its center is at the true center. I'm going to assume that's 22. Again, that's in white because I don't know it. I know its spread would be the spread, the standard deviation of the population divided by the square root of n. And I know if that n is at least 30, the central limit theorem tells me this will be a normal curve. All right, so here's where we're going to start doing, building a confidence interval. Let's just talk about the nature of this sampling distribution. The one blue dot in all the white dots, those white dots represent the gazillion different samples I could have chosen. Let's say I chose 100 workers and said, hey, how much do you make? Out of everybody in America, there are countless ways I could choose 100 people. I mean, millions upon millions upon millions. So I have made a gazillion little white dots to show these true numbers would be close to 22 if the number is actually 22. And I'm just going to keep it simple with a standard deviation of 1. Now, if I'm really the person writing that article we just looked at, the one thing I know is the $20.70 that I got for my average. I am reporting it like it's a fact. Here you go, it's $20.70. How do they know that? They don't have any idea if that's right. But they are confident to some certain percentage. Usually we're going with 95%, so follow me. Would you agree that 95% of all of the dots in this normal curve are between 2 standard deviations to the left and 2 standard deviations to the right? We learned the empirical rule last semester, and it said if you go 2 steps left and 2 steps right of the center, then that's 95% of all data points. Now in this case, each data point is one sample of size 100 from all of the people in America who have jobs. Now, here's where we go. Let's just take our blue dot and let's go left and right 2 steps. All right? Here's our little dinosaur saying, I love you this much. He has stretched his little fake arms out because he's a T-Rex with short arms. And he is reaching out 2 standard deviations left of wherever he is and 2 standard deviations right of wherever he is. Now, he has a 95% chance of ending up between the 2 purple lines. All right, he is one sample of size 100. So there's a 95% chance he's somewhere in here. And there's a 5% chance that he's somewhere out here or somewhere out here, right? That 95% in the middle means there's 2.5% on either side. Now, there is a 95% chance that I'm in the middle. If I'm in the middle, would you agree that there's a 95% chance, let me restate that sentence. If there's a 95% chance that I'm in the middle, then there's a 95% chance that dinosaurs' arms are going to cross the red dashed line. Think about that. If I put the dinosaur at any dot and 95% of them are in here, then that means if I'm on any one of those dots, my dinosaur's arms, cross the red dashed line. So a confidence interval, what's going to happen is we're going to get our number, our one blue number that we know, and we're going to stretch our arms out, and we are going to catch, or we are going to contain the true unknown population mean 95% of the time. All right, think about it. If dinosaurs are way out here to the right, which only happens 2.5% of the time, his arms don't touch, right? If he's way over here to the left, his arms don't touch the red line. But if I did this study and I go right here and put the dinosaur on the blue dot, his arms do touch the red line because he is within the middle 95%. All right, I hope that little illustration helps. But what we're going to do is we're going to get our number that our statistic shows, that our sample gave us. We're going to reach our little arms out, depending on a percentage. Usually it's 95. I'm going to reach my little arms out, make a nice big net in which I want to catch the true value. So really what this article should have said is this. The average is somewhere between, let's call it $20 and $21.40, and I'm 95% sure that's the case. All right, they just report it as fact, but in reality, they're going to give you a certain window and a certain amount of definiteness. That's not a good one. Certainty, a certain amount of certainty that they actually caught it. All right, that was a little bungle there, but hopefully you get the idea. If your sample turns out anywhere in here, which it will 95% of the time, then your dinosaur is going to touch the true mean. And your dinosaur arms are upper and lower cutoff points that are called a confidence interval. All right, so how is it made? We get a statistic from the sample. And we add and subtract from that statistic all of this. This is called the margin of error. Everything we're doing today will apply to proportions and means. And when you hear, maybe you've heard a report on the news that says something's 44% plus or minus 2%. So really they're saying, I'm pretty sure it's somewhere between 42 and 46. The critical value will be based on how sure you want to be and whatever distribution you're dealing with. And the standard deviation of the statistic, this is just the adjusted standard deviation that we worked with last chapter. I'm just going to put depends because there's a couple things that will go into finding that critical value. And in our future videos, we'll talk about that. So what I'm going to do is take my number, I'm going to add and subtract the margin of error, and then I'm going to say I'm 95% confident that the true population unknown parameter is between here, point A and point B, and that's what I'm going to report. All right, so we're just doing basics now, so I know there's some gray area left to how to calculate it and all that. We'll get to that. How to interpret it. You need to write this wording down, and you need to memorize it. What you want to say when you are done is this. We are blank percent confident that the interval from blank to blank, right? That's going to be created by taking your statistic, adding and subtracting your margin of error, captures the actual value of context here. This is the true unknown parameter. But you don't just say the mean. You say parameter. Sorry about that. So what you're going to say is I am 95% confident that the interval $20 to $21.40 captures the actual value of the mean hourly wage of U.S. employees. All right? Unknown parameter goes there. Think about it. I'm 95% sure my dinosaur is going to cross the red line with his big long arms. So I'm 95% sure that crossing the line, he has captured in his grasp the true value. All right? Did these guys capture it with their study? If all this is true, yeah, they were a little low, but they captured it. All right? Their dinosaur's arms touched the red line, which is my goal, to report to the people what's the unknown mean that really I don't know, but I'm trying to sum up. All right, so memorize that red, and we'll fill in the blanks with all of our specific examples. So here's the deal. If you're reporting this, you want to be able to tell somebody with relative certainty, right? If you want to be 99% sure or 99% confident, think about it this way. I've got a net and I want to catch a butterfly or a fish or whatever. If you want to be pretty sure, 99%, almost certain you're going to catch it, use a bigger net. So if you want to be 99% confident, just use a huge net. Give a big wide margin. Why is that a problem? Why wouldn't I always just do that? Well, if you're doing that, then you're saying to the people, I am 99% confident that the true value is between $15 and $25. You're like, thanks a lot. 15 to 25, that's a huge spread. You say, well, I wanted to be pretty darn sure. You have to find the balance. Usually that balance happens at 95%. You can do any percent you want, and we will go on to do that. Usually it's something like that, right? How sure do you want to be? 99, 95, 90? You could do 80 if you wanted to. But the more sure you want to be, the bigger the net you have to cast. All right, so then the people are thinking, well, you're pretty sure, but that's a huge range, right? I am 99% confident that the average high school student is between 1 foot and 17 feet tall. I'm pretty sure that's the case. Well, thanks a lot. 1 to 17 feet. Everybody knows that, idiot. You don't need to have that much confidence if you're going to have that big of a net. A big net's not good if you want to give an accurate number. All right, confidence interval conditions. We've talked about conditions in the sampling distribution sections. We're going to just add a little bit. What needs to happen is 3 things. Random. All right? We need, and I've said this lots of times, we need our sample to be a random. We do not want any bias in our sampling. We do not want a messed up experiment. We need an SRS, a simple random sample. You're going to write SRS as a check 1,000,000 times this semester. We need it to be normal. Notice we started with a white normal curve, and that's based on the same conditions that we used last chapter. If it's a mean, either the population is normal or sample size is at least 30. Remember the central limit theorem. If it's a proportion, NP and NQ are both greater than 10. All right, this is not new. All right, independent. We did normal and independent already. We're just adding in the random, but we're just reviewing the independent right now. If you want your selections to be independent of one another, same deal as before. You don't want to sample too much of your population. If you look at too much of it, then your population that you're drawing from at the end is much different than the one you started with. But if you keep it less than 10%, you have not adjusted it too much to mess with our numbers. As I've said before, in real life, you want to see as many people as you can, but for our purposes to do these calculations, we don't want to choose more than 10%. Now, we'll talk about several cautions. I just want to get one right here. Your margin of error that naturally happens because of sampling variability. These people that I'm kind of giving a hard time because they said $20.70 in a world where the actual number is 22. Again, I made that up. But let's say it's the truth. They're saying 2070 like it's a fact. If it's not really the case, are they doing a bad job? Well, no, they just happen to get a number on the left side of center. Right? They just as easily could have said it's $22.70. There is some natural variability that will happen. This margin of error right here it's only accounts for natural variation. It does not count for any other mistakes or bad samples or errors. So the margin of error you already have that much variability to worry about under perfect conditions. All right. So when you do a confidence interval, you're assuming everything went well, and we still have a certain size net, like right here, that we have to deal with. I still have to say, well, it's between 12 and 14. I'm not sure. That's just because of the variability. If you've got a messed up sample, non-response, under coverage, bias in any of those ways, then your margin of error is even worse. All right. We will get to more of these, but for the sake of time, I'm going to cut it off here. All right. This is just the basics. Like I said, you should be left with some questions. How am I going to calculate these numbers? What the heck's a critical value? How do I get my window? All to come. This is just to get you familiar with our little dinosaur friend here. 95% of the time, he's somewhere in here, so his arms touch the red line. I like moving this dinosaur around in circles if you haven't noticed. 5% of the time he's over here or over here, and he's not going to catch it. In which case, you go out on the news and you say, hey, the average is somewhere between 24 and 26 because my sample was 25. Is it between 24 and 26? No, you missed just by chance. You were the unlucky one that happened to get a sample of well-paid people. And I better stop there. I could talk about this dinosaur forever. So, confidence intervals day one, out.